So I've been asked to prepare just a little video on the partial differentials. So when we have a partial differential, instead of writing it dy by dx, we write deltas, little deltas. This means that we have a partial derivative. And we also show it in the bracket with the subscript to say what value we're keeping constant. So for example, if I was to have the function y is equal to x squared plus zx plus z squared, a nice and simple function, I can differentiate this with either respect to x or as respect to z. So if I were to differentiate this with respect to x, I would write delta y over delta x, and I'd put that in brackets, and I would have a little z down here to say that I'm going to differentiate this whilst keeping z constant. So anywhere in this differential that I see a z, I'm just going to treat it as if it was a constant, as if it was a number. No difference to that. So if I were to simply differentiate this with respect to x, differential of x squared is 2x. Here, the differential of zx, well, this is just the same as me saying the differential of 3x or 5x or something like that. Z is just a constant. Differentiate x, it disappears. So this is z, and I differentiate a constant and it disappears. I could also differentiate this function with respect to z. And this time I have a subscript x to say that I'm keeping x constant. So if I was to differentiate this with respect to z, x squared, that's just a constant. I differentiate a constant, it disappears. Zx, so this is just a constant multiplied by z. So differentiate z with respect to z, that just becomes 1. So this is just a constant x. And then I have the differential of z squared with respect to z. So this would be 2z. Now, I can also carry on and have second differentials of this function. So I could differentiate this dy by dx again. And in this case, we write d2y by delta 2y by delta x squared. And this is again at constant z. So I'm just going to differentiate this function with respect to x. So I differentiate 2x, the x is just going to disappear, it's going to leave me with 2. And I differentiate a constant, and that just leaves me with nothing, 0. I can do the same thing here and find the double differential of y with respect to z, which we would write as delta 2y over delta z squared, subscript x at constant value of x. Anywhere where x is, it's a constant, so if I differentiate it, it just disappears. So here, x on its own would give me a constant differential is just 0, differentiate 2z, and therefore I end up with just 2. The final one that I could do is I could differentiate dy by dx and differentiate that with respect to z, or I could differentiate dy by dz with respect to x. So I'm going to just do that though on a slightly more difficult example so that we can see that in action a little bit more. Okay, so now I have a new function, y is equal to 5x cubed plus 3x squared z squared plus z to the 4 plus 6. And what I'm going to do is I'm going to differentiate this first off with respect to x whilst keeping z constant. So delta y divided by delta x at constant value of z. So this is just going to be 15, 3 times 5, x squared, and then plus I'm going to differentiate the x here, z's just a constant, so this just becomes 6x z squared, I differentiate z to the fourth, but if that's a constant, that just disappears. And I differentiate 6, that's just a constant, so that disappears as well. As I said before, I can also differentiate this with respect to z at constant value of x. This is my partial differential with respect to z at constant value of x. In this case, this is just a constant. So this one disappears. I differentiate this term here, and I end up with 6x squared z. I differentiate this term here, which would become 4z cubed, and I differentiate this term here. This term just disappears, it's just a constant. So if I just work out the double differentials of those in each case, so delta 2y divided by delta x squared at constant value of z, that is equal to 30x. So this is just my differential here. I've just multiplied the 15 by the 2, taken 1 off this power. And then I'm going to differentiate this term. If I differentiate x, z is just a constant. So this time I'm going to have 6z squared plus 6z squared. Here, if I differentiate delta y by delta z with respect to z again, so d2y by dz squared, at constant value of x, so if I differentiate this, differentiate with respect to z, so I'm going to take 1 off the power of z, so this is going to be 6x squared, and I differentiate this one, that's going to leave me with 12z squared. So I've just taken the 3 down to the front, multiplied the 2 together, and taken 1 off the power. Now, as I said before, the other example I can do is d2y by dx dz. So this is me differentiating this function here with respect to y. We should read from right to left, the order that we're doing them. Left to right, rather. Left to right. So I'm going to differentiate this function here with respect to z. This here is just a constant, so this is going to disappear when I differentiate with respect to z. If I differentiate this one with respect to z, I end up with 12xz. So I've just taken this 2 down to the front, taken 1 off the power of this z, so this is leaving me with 12xz. That's all I get when I differentiate twice delta x, delta z. If instead I was to differentiate the z first and then differentiate with respect to x, what do I get? And so here I'm going to differentiate the x, so this is going to leave me with 12x. The z is just a constant, so it stays, and if the z is a constant, this term here disappears, it's just a constant. And we can see that these two terms are identical. When we double differentiate, it shouldn't matter the order we do it. It's commutative. It doesn't matter the order we double differentiate. And so we can show that these two are the same thing. And that's the important thing that matters. So just another example. Here, instead of writing, for example, y is equal to, I've just said the function, which is a function of x and y. And this is what it's equal to here. So I can differentiate this function, df of xy by dx at constant value of y. If I do it at constant value of y, sine y is just a constant. I differentiate this to become 2x sine y. Here, differentiate x squared. Y is just a constant, just as if it's just a number. And so this becomes 2xy. And here, I differentiate this value here, and this becomes 10x. I can now differentiate that with respect to y instead of x. So this is time I'm at constant value of x. This is what this subscript here means. And so if I differentiate this with respect to y, x squared is just a constant. It doesn't matter. So I differentiate sine y. That becomes cos y. and then I'm going to have plus. If I differentiate this, x is just a constant, so it stays x squared. Differentiate y with respect to y, that's just 1, so this is just an x squared term. And this is just a constant term here as well, so when I differentiate that, that becomes 0. If I differentiate this function with respect to, d2f of xy by dx squared at constant y, so this is just me differentiating this again. Differentiate x, which is just 2 sine y plus 2y plus 10. You can see how simple that is. And I can do the same thing for, this is dy squared at constant x. So this is me differentiating this one again. So this just becomes minus x squared sine y. I've differentiated a cos, it's become minus sine. X squared is just a constant, and if x squared is just a constant, it disappears when I differentiate this term here. So I hope that's making a little bit more sense to you. I've just differentiated here with respect to 2 terms, but I can have as many different terms in there as possible. So when I spoke about the ideal gas law in the lecture, we had 3 different variables there which I could differentiate with respect to. There's no limit. And if I have multiple variables, the ones that I've kept constant, I just separate with a comma outside of this bracket. I hope this has been useful. Feel free to contact me if you need any more help.